So let's say we have a cup of water and we put in, let's say, some mineral fluorite, and we let fluorite dissolve. What we're going to do in this video is we're going to take a look at how much of that mineral of fluorite will dissolve using KSP values and what the concentrations of the various ions would be in that water that's sitting there in that cup. So fluorite, that is the mineral CaF2, and it will dissolve to form calcium ion in aqueous solution with a 2 plus charge and two fluorine atoms, fluoride ions, also in aqueous solution of a 1 minus charge each. So the key thing here is we have molar abundances. Anytime we write this, we're always looking at moles. 1 mole, or essentially if you want to call it 1 molecule of CaF2, that would give us 1 mole of calcium ion and 2 moles of fluorine atoms. So that's the way it's going to dissolve. The KSP for this would be written as the concentration of calcium 2 plus ion in aqueous solution multiplied by the concentration of fluoride ion raised to the power of 2. Remember that anytime we write an equilibrium constant of any kind, including a KSP, whatever coefficients we have out here in front of something like fluoride ion, that becomes an exponent in this kind of expression. Well, what we're going to do to calculate the values for KSP. Well, first we need to look up a value of KSP. Well, in a table, I found a value of PKSP of 10.6. So if we want to recover the KSP would be 10 to the minus 10.6, and that's a value of about 2.512 times 10 to the minus 11. So what we're going to do is let this thing be equal to the concentration of calcium multiplied by the concentration of fluoride ion squared. And we're going to just play a little mathematical trick. We're going to let the concentration of calcium be X in moles per liter. And if the concentration of calcium is X, then when we divide 1 mole of fluorite to get calcium ion plus 2 fluoride ions, then whatever the concentration of calcium is, the concentration of fluorine must be 2 times that amount, right? If we have 1 mole of calcium here, we must get 2 moles of fluorine here. So we can write, if the concentration of calcium is X, then the concentration of fluorine must be 2 times X. And so we can combine these. Let's combine this value here. This is going to be equal to this product. This is going to be equal to X times 2X squared, putting in X for that and 2X here, and that will be 4X cubed. Let's erase the chalkboard. This 4X cubed is going to be equal to this. So 4X cubed is equal to 2.512 times 10 to the minus 11. We can say then that X cubed is equal to 6.28 times 10 to the minus 11, and to get rid of the 3, we can raise this to the 1/3 power, and so we get X is equal to about 1.845 times 10 to the minus 4. Now remember, X was defined as the concentration of calcium in units of moles per liter. So now this leads us directly to the concentration of calcium. So let's take this value and then transfer it over to our next page, raise the chalkboard. Here is our glass of water here, and we have a little octahedron of fluorite sitting down at the bottom of that glass of water. So what would be the concentration of the various cations? Well, for calcium ion in aqueous solution, we've just calculated the concentration would be 1.845 times 10 to the minus 4 moles per liter. That was our value for X. Remember, we said this whole thing is X, and we just found out that X is equal to this. But for the dissolution of fluorite into calcium and fluoride ions, whatever the amount of calcium we get, we must get 2 times the amount of fluorine. So the concentration of fluorine in this solution here would then be 2 times 1.845 times 10 to the minus 11. And that would be equal to about 3.69 times 10 to the minus 4 moles per liter. So there, we've used the KSP value to get the concentrations of calcium and fluoride ions for a very special case. There are some caveats. We assumed that we had pure fluorite, otherwise we could not use the KSP value. And we're also assuming, though, that we have pure H2O, that there's nothing else that's in that water that might affect this equilibrium. What else could affect it? Well, let's say we had some sodium fluoride that was dissolved in the water. Sodium fluoride dissolves very strongly to form sodium ions plus fluorine ions. And if we had sodium fluoride dissolved in the water, then that is going to increase the amount of fluorine. But if we increase the amount of fluorine, that's going to react to bind with the calcium to decrease the calcium and increase the amount of fluorite. So by adding some sodium fluoride to the system, especially something that can dissolve to give us large amounts of fluorine ion, we would force the reaction in this way, increase the amount of fluorine because of this new source of fluorine, but then using up some of the calcium and fluorine in the process, which would drop the amount of calcium and increase the amount of fluorite. So there are other things that might be dissolved in here that can affect this reaction. So keep in mind, we're thinking about pure water and pure fluoride in the system, and that affects these calculations. Let's end to take a look at what's going on with the fluoride itself. So we have 1 mole of fluorite that is dissolving to form 1 mole of calcium ion and 2 moles of fluoride ion. Well, if this is X and this is 2 times X, right, that we've got 1 mole of calcium, well, this would also be X. We would have 1 mole of fluorite giving us 1 mole of this and 2 moles of this. So if we want to know how much fluorite will dissolve in our system where we have pure water, we can calculate this as a function of the weight of fluorite that will dissolve by making this calculation. Again, we take the value of X, which is still 1.845 times 10 to the minus 4 moles per liter, and we'll apply that to the fluorite. So the fluorite, we would have 1.845 times 10 to the minus 4, in this case, moles of CaF2 per liter. And if we want to know how much will dissolve in terms of the number of grams, we can use the molecular weight of calcium fluoride. So the molecular weight is equal to 78.07 grams per mole. Now let's just write that over here. We would have 78.07 grams per mole. Notice that here the moles will cancel, leaving us with grams per liter. So if we'll multiply this times this, then we would get a value of 1.44 times 10 to the minus 2 grams per liter. That is our solubility of fluorite. And again, not just under any conditions. The values that we looked at, we started out with PKSP values that were determined at 25 degrees centigrade, which is kind of our standard for room temperature. But what's also kind of a hidden assumption is that we're looking at the dissolution of pure water. If we've got a much more messier system, a source of calcium or a source of fluorite could change this value for solubility. So the solubility that we've calculated is an ideal case. Doesn't mean that it's useless. It's very rare that, let's say, your drinking water is going to be pure H2O, unless you're drinking distilled water from off the shelf of the supermarket. But it is a starting point to take a look at how much of a given material might dissolve in a given amount of water and the concentration of ions that might be derived from that dissolution.